This is the Choose Your Own Adventure lab, which I will be discussing collisions for. Now what we're going to do is analyze the collision between two very hard and solid billiard balls and determine what type of collision occurs between them. Now we want to see if it's elastic, inelastic, or maximally inelastic. And we want to see how we can use the energy principle and the conservation of momentum to determine the type of collision. And then we want to take this and model it in Python to see how it compares to our observations. So after analyzing the motion of the two balls, we come to the conclusion that this collision is very close to elastic. Now it is not perfectly elastic because a true perfect elastic collision is not very easy to obtain in an observational model. We came to the conclusion that because Ke final is approximately equal to Ke initial, energy was conserved in the system, indicating that it is a near elastic collision. Now what are we actually working with? In this case, we'll be working in the point particle system, and we'll be working with momentum and the translational kinetic energy. Before we start, we must first note that in a fully elastic collision, kinetic energy is conserved, which means Ke final is approximately equal to Ke initial. This also means that the total energy in the system is conserved, so delta E equals 0. In an inelastic collision, however, kinetic energy is not conserved, so in this case, Ke final would not be equal to Ke initial. Now we can take a look at the actual video that is tracked in Tracker, where we have a calibration equal to the width of one billiard ball, which is 0.057 meters. And we have also set the origin equal to where the second ball's position initially is. Now had I decided to orient these axes, especially the x-axis, in a different way, we would see that the momentums in this case would be opposite because the velocity would be negative rather than positive. Now when we run this, you can see that ball 1 approaches ball 2 with a constant velocity until they strike each other, at which point ball 1 comes to rest and ball 2 moves off with a velocity equal in magnitude or approximately equal in magnitude to the initial velocity of ball 1. So now we can take this data and plug it into our equations. Now to begin, we first calculate the velocity of the first ball while the second is at rest. To do this, we just use a simple equation delta r over delta t equals velocity. We take the data that we just observed in Tracker to get a constant velocity of 2.38 meters a second for the first ball. We use the same equation to calculate the velocity of the second ball after the collision and after the first ball comes to rest. By doing this, we get a velocity of 2.325 meters a second, so we can now compare momentums and energy. Now we already discussed the constraints for elastic and inelastic collisions. Now we must use translational kinetic energy formula to calculate the energy for each ball. Now this is given by Ke equals 1 half mv squared. So delta Ke for each ball will be equal to 1 half m times v final squared minus v initial squared. Now we know that for the point particle system, delta Ke of the system must equal 0. We can also confirm the collision is elastic with a conservation of momentum, where the initial momentum of both balls is equal to their final momentums. Now what do we actually find? When we make the calculations with our velocities from earlier and a given mass of 0.17 kilograms for each ball, we get the Ke initial for the first ball equals 0.481474 joules. The second ball starts at rest, so its initial energy is 0. We then calculate the new energies after the collision to get that the Ke for the second ball in its final state is equal to 0.46 joules, while the first ball has come to rest, so its final energy is 0. We can see that this is very close to elastic, as 0.4814 joules is approximately equal to 0.46 joules. We can still assume that this is elastic because there are always minimal factors that can skew the results, such as human error, so when we obtain approximately close answers for this, we can still assume that it is elastic. We can confirm this further by proving that momentum was conserved as well. We need to know that delta P equals 0. In our case, we need to be approximately close to this to show that this is elastic. When we calculate utilizing the mass of each ball, as well as their initial and final velocities, we come with the answer of 0.009 kilogram meters per second. This is a very small error that could be attributed to human error, and thus we can say that delta P equals 0 so that this collision is elastic. Now we want to try to model this in Python. We set up the initial conditions of each ball's mass equaling 0.17 kilograms and set the positions and velocities equal to what we obtained from Tracker, where the ball's initial position is negative 0.166 meters and ball 2's position is at the origin, and the ball 1's initial velocity is 2.38 meters per second, which we calculated earlier. Now in the while loop, we first see that we set each ball's velocity equal to its current velocity. This is because initially they are not changing. However, in the if statement, we can see that if they do collide, then we set the ball 2's velocity equal to ball 1's velocity because all the energy from ball 1 is transferred to ball 2. Then we set ball 1's velocity equal to a vector of 0, 0, 0 because it comes to rest. Then you can see that we calculate the kinetic energies of each ball with the equations we discussed earlier as well as the momentums. And then we update the positions by adding their initial position to the velocity times delta t. So what did we find with Python? In this case, the model is a perfect example of a perfectly elastic collision. This is something that does not really occur in real-life systems, however. You can see in this graph that the blue line is equal to the kinetic energy of the first ball, while the red line is equal to the kinetic energy of the second ball. And you can see that the yellow line plotting the change in kinetic energy is always equal to 0, meaning that kinetic energy is conserved, meaning that this is an elastic collision. So in conclusion, we were able to prove that it is very hard for a truly elastic collision to occur in a real-life scenario. However, we were able to show that in this case, very hard solids such as billiard balls can obtain an approximately elastic collision.